This video presents a general principle of learning and its application for reconciling Einstein's general relativity. The human brain has an amazing power at solving different cognitive tasks, ranging from visual perception, playing chess, building airplanes, to the discovery of the energy and mass relation E=mc². However, up to now, nobody knows how the brain works and what is the principle underlying its power. In this presentation, a general principle of learning is proposed to understand intelligence like the human one. It will attempt to reveal the logical structure underlying intelligence so that we can implement it using machines to help us to smooth out the differences in individual intelligence, just like machinery to individual physical power. It can help us to build better human societies for equality, peace, and prosperity. You cannot understand bird flight by studying only feathers. In the same vein, you cannot understand intelligence simply by studying neurons and their wirings. In both of the cases, we need to find out principles underlying them instead of their physical embodiments. The principle underlying intelligence is likely to be discovered by studying the nature of the problems being solved by it instead of its implements in nature as biological neural networks. The principle to be uncovered should be broad enough to explain low-level perceptions as well as high-level rational and analytical thinking. In this presentation, a general principle of learning is proposed for understanding intelligence. Its application in physics is also presented in an attempt to solve the most challenging intellectual problem of humankind, that is, unifying Einstein's general relativity with quantum theory. Everything in the universe has an intrinsic logic structure, intelligible and comprehensible only by intellectual thinking. The true power of intelligence is the capability to discover those structures so that they can be used as the models to solve different problems. The human brain has an amazing power at solving different cognitive tasks, ranging from visual perception, playing chess, building airplanes, to the discovery of the energy and mass relation E=mc². Any specific solution for any specific problem coined by human brain is just a result of human intelligence, not intelligence itself. To have artificial general intelligence, it is critically important to find out the principle underlying this general learning capability of the human brain. Without understanding the principle, any learning theory is just a cookbook of different heuristic methods. They are just a collection of magic tricks, lack of any logic foundation for explaining their successes or failures at solving real-world learning problems. The essence of intelligence is goal achieving. Specifically, the main concern of an intelligence system is to achieve certain goals or objectives, that is, to change the world into its desired states. This is done through understanding and planning. The understanding part is concerned with making predictions about the world, and the planning part adds the generation of plans for goal achieving on top of understanding. The core of intelligence deals with understanding, planning, and goal achieving. The central element in understanding is the model of the world, also known as the knowledge of the world. The model is the embodiment of knowledge for understanding the world, making the world less unpredictable. Its main usage is to make all kinds of predictions about the world. One of the primary sources of knowledge is learning. The essence of learning is generalization. Specifically, the main concern of learning is to discover a model of the world by using observations and experiences. The discovery and the refinement of the model is mainly through generalization. Generalization makes the predictions for unseen situations possible. The core of learning deals with generalization, predictions, and model construction. The sole purpose of our knowledge is to let us to make predictions about the world. With knowledge, the world is less unpredictable. More knowledge we have, more accurate predictions we can make. A body of knowledge is better than another one if it makes more accurate predictions than the other. Intelligence is nothing more than the ability to make predictions by using a body of knowledge and the ability to generate plans to change the world into desired states. Making prediction is still required at the planning stage. Therefore, prediction is critically important for any intelligent system, both at the understanding stage as well as at the planning stage. Constraint is the most fundamental element of knowledge. A constraint defines a correlation of a set of variables of a problem. A constraint can be expressed in a pure analytic form or a lookup table form. It can be a law of nature that govern the universe, such as F equals ma or E equals mc square, or the dependence between two numeric variables defined in terms of covariance. The knowledge of any domain or any problem can be viewed as a collection of constraints defined on a set of variables, called a constraint model. This is a quite universal representation for any body of knowledge. The constraint model is a massively parallel, distributed computing system for understanding the world. It is postulated here that the human brain can be viewed as a gigantic constraint model with lots of submodels, one for each category or class, organized hierarchically in a recursive way for understanding the world. It is also postulated that the cortical column of the human brain corresponds to the constraint variable in the constraint model, which defines a set of mutually exclusive states of the same variable as its fundamental. It is important to realize that constraint model can be used as a universal framework for knowledge representation. There are two essential parts in a constraint model, namely, variables and constraints. They together define a graphical structure with the variables as nodes and the constraints as the connections. It is also known as Markov random field, probabilistic graphical model, and factor graph in many other literatures. Usually, what we have at hand are observables, not those variables where the constraints are defined upon. Those variables are called the constraint variables here. The observables are the projection of the constraint variables through some viewer-dependent perspective and possibly polluted further by interference, noise, and disturbances. Without loss of generality, assume that the world can be described by a probability density function p, x. Assume further that a constraint model is used to approximate the probability density function p, x. To be more specific, let x be the set of constraint variables, y be the set of observables, and psi y to x denotes the mapping from the observables y to the constraint variables x. Let a non-mutually disjoint partition of x be denoted as pi x, each of its element is a subset of x, denoted as xi. Obviously, the union of xi for xi in the partition set pi x equals x. For each xi where xi in the partition set pi x, there is a constraint defined on xi, which equals to the marginal distribution of px on the subset of variables xi, denoted as pxi. With those notations and definitions, we can have a generalization of px as its approximation as follows. Equation 1 is the most fundamental, canonical form for knowledge representation. It is called the canonical constraint model of px, denoted as p plus x. Others, such as relational database, differential equations like Maxwell equations, and polynomial equations like Newton's mechanical laws, can be viewed as its extended or reduced forms. It serves as the foundation for generalization. As mentioned before, the essence of learning is generalization. The canonical constraint model described by equation 1 indeed defines a generalization for the original probability density function px. It is called the canonical generalization here. In the following discussions, let the entropy of px be h_px and let the entropy of the canonical generalization p plus x be h_p plus x. For the marginal distribution pxi, its entropy is denoted as h_pxi, and for p plus xi with h_p plus xi. The canonical generalization p plus x given in equation number 1 has the following important properties. Property number 1, for any x, when px is not equal to 0, then p plus x is not equal to 0. Property number 2, for any xi, there exists a subset xi such that xi is in the subset xi and h_pxi is equal to h_p plus xi. Property number 3, for any subset xi, h_pxi is less than or equal to h_p plus xi, in particular h_px is less than or equal to h_p plus x. Property number 4, px equals p plus x. If and only if h_px equals h_p plus x. That is, the global minimum of h_p plus x is px. From those properties we can see that the canonical generalization is always an underfitting estimation to the original function px. Unlike many other learning models, it never has the overfitting issue. From the property number 4 of the canonical generalization, 1, we can see that the objective of learning when the canonical generalization is used is to minimize its entropy. The smaller the entropy is, the better the generalization is at estimating the original density function. That is, it is less overgeneralized in this case. In other words, the objective of learning when the canonical generalization is used is to find the one that is least general using available training data. This is called the principle of least general generalization here. Generalization error: given a canonical generalization p plus x of a probability density function px, the generalization error is defined as the Kullback-Leibler divergence from px to p plus x. That is, the generalization error equals to the difference between the entropy of the canonical generalization and the entropy of the original probability density function. Note that the divergence may not exist if p plus x is not a canonical generalization of px. The generalization error equals 0 if and only if p plus x equals px. In this case, the entropy of p plus x equals the entropy of px. The entropy of the constraint pxi is It is important to note that the model entropy of the canonical constraint model described by equation 1 determines the prediction accuracy of the model. A lower value for the model entropy leads to higher prediction accuracy. Therefore, minimizing the model entropy described by equation 2 is the ultimate objective of learning. At the same time, the entropy of a constraint determines the learning efficiency to acquire the constraint from training data. A lower value for the constraint entropy leads to a higher rate of learning efficiency. In other words, less training data is required in this case. Based on these observations, we have the principle of learning as follows. The prediction accuracy of a constraint model determined by its entropy can be improved by mapping the existing observables to another set of variables and detecting the associations among those variables using observations and experiences. Everything in the universe has an intrinsic logic structure defined by laws of nature. That is, everything in the universe has a mechanical explanation including the human intelligence and the universe itself. Different things in the world may have different intrinsic structures. All we see and feel are simply the manifestations in space and time of variations of those intrinsic structures. To truly understand the world, it is important to reveal those intrinsic structures. This is the ultimate goal of any learning algorithm. An intrinsic structure can be defined by a set of intrinsic variables together with a collection of constraints defined on those variables. Therefore, it is also called an intrinsic constraint model. The projection from intrinsic variables to observables is defined by nature or the problem at hand. It is usually unknown completely or partially to a learning algorithm at the beginning. One of the critical tasks of learning is to figure out the inverse of the projection, called intrinsic mapping here. It defines the mapping from observables to intrinsic variables. Usually, it is context-sensitive, different from those context-free feature extraction used by classical machine learning. This context-sensitive character gives the constraint model much greater representation power than any other models which are based on context-free feature extraction. For visual perception, in particular, intrinsic mapping falls back to correspondence mapping, for example, nose-to-nose and eye-to-eye for facial recognition, and wheel-to-wheel and window-to-window for car recognition. The objective of a learning algorithm is to discover the intrinsic constraint models together with its associated intrinsic mapping for a specific problem at hand. To achieve that goal, a learning algorithm needs to discover the intrinsic variables from observables, and to detect the constraints imposed on those intrinsic variables using observations and experiences. The intrinsic constraint model, defined by laws of nature, has the following two very important mathematical properties. Theorem: the intrinsic constraint model for any problem has the minimum model entropy as well as the minimum constraint entropy for each constraint of the model. The model entropy is also called the global entropy and the constraint entropies are also called the local entropies. The first property leads to the minimum randomness of the model, the degree of freedom. In other words, it says that the intrinsic constraint model has the highest accuracy at making predictions. The second one leads to the minimum learning complexity and the minimum representation complexity. In other words, it says that the intrinsic constraint model requires the minimum number of training samples to reach a specified prediction accuracy and the minimum number of parameters to describe the model. The intrinsic variables can be projected into other variables, such as observables. So are the constraints by truncating, splitting, and joining. Any projection of the intrinsic variables and constraints leads to a new constraint model, called a projected constraint model. The theorem tells us that any projected constraint model may have increased global entropy as well as increased local entropies. As a consequence, the prediction accuracy by using the model will be degenerated, so is the learning efficiency. Therefore, it is critically important for a learning algorithm to discover the intrinsic variables for a given problem for the sake of the maximum prediction accuracy and the maximum learning efficiency. As discussed before, the intrinsic constraint model to a specific problem has the minimum global entropy and minimum local entropies. In other words, it has the maximum prediction accuracy and the highest learning efficiency. Specifically, given a specific amount of training data, the constraint model built upon the intrinsic variables has the minimum global entropy compared with any other constraint model built upon variables other than the intrinsic ones. That is, the intrinsic constraint model has the maximum generalization power. It can achieve a targeted prediction accuracy with the minimum amount of training data. Therefore, it is critically important for a learning algorithm to discover the intrinsic variables to a specific problem for the sake of generalization power maximization. It is important to note again that the intrinsic constraint model has the maximum generalization power. As mentioned before, the ultimate goal of any learning algorithm is to minimize the model entropy given in equation number 2. Combining it with the discovery of intrinsic variables, learning can be formulated as the following optimization problem. That is, the objective of learning is to discover a mapping from the observables y to another set of variables x, and a partition of x as pi x such that the entropy of the constraint model defined on them is minimized. In particular, the intrinsic model is the optimal solution to the minimization problem described by the formula 3. To solve the above minimization problem, global optimization is indispensable. Replacing a global optimization method by any local optimization algorithm, such as classical local search or gradient descent, will lead to severe degradation of the learning efficiency and prediction accuracy. In other words, the generalization power of learning will degrade significantly as a result of replacing global optimization by local optimization. The process of discovering the intrinsic variables specific to each cognitive task is the key element for any learning theory and method to have the true power of intelligence, that is, the capability to figure out different solutions for different cognitive tasks. Such a process plays the mission-critical role at understanding the world, which has all kinds of objects with vastly different intrinsic structures at different scales and abstraction levels. It is the most fundamental missing piece in all existing learning theories and methods. Without the discovery of intrinsic variables, any learning algorithm may suffer a severe limitation on its generalization power in practice as well as logic completeness in theory. Therefore, it is desirable for any classical learning algorithm to add the discovery of intrinsic variables into its learning process to improve its learning efficiency. Pedro Domingos in his recent book summarized that there are 5 major tribes of machine learning. They are symbolists, connectionists, evolutionaries, Bayesians, and analogizers. Each one contains some elements of learning. However, none of them touches the key element of learning, that is, the discovery of intrinsic variables through the minimization of the objective function. 3. Without this key element, any learning algorithm will be just like shooting in a dark room with their learning power greatly limited. For example, current popular deep neural networks demand million times more labeled training samples than human vision. It is a significant degradation in terms of generalization power. The fundamental reason for that is the missing of the discovery of the intrinsic variables. Adding it to any deep learning algorithm can easily boost up its generalization power remarkably. How to discover intrinsic variables from observables. Note that a variable is just a set of mutually exclusive values or states. To discover intrinsic variables from observables, we need to break up observables into their states or more by value factorization and then recombine them to form new variables in order to minimize the objective function of learning defined in equation 3. The intrinsic variables are discovered when the global minimum of equation 3 is found. In general, the Goldilocks principle can be used at selecting training samples to ensure a fast convergence to the optimal solution of the master minimization problem defined by equation 3. Making analogy as the core of cognition and unification as the core of discovery in physics can be viewed as two important techniques in a similar vein at discovering intrinsic variables. Any theory and methods for understanding and discovering the intrinsic variables are the most important intellectual properties for any company working on machine learning. There are two incompatible foundations for physics today, namely, quantum theory and Einstein's general relativity. Moreover, there are many other troubling issues with general relativity like black hole problem, flatness problem, cosmology constant problem, singularity problem, vacuum energy problem, and quantum normalization problem. It is a call now to scientists to reconcile Einstein's general relativity with quantum theory. Einstein's general relativity is a geometric approach to understand gravitation. However, it failed to bring equality to all inertial frames at the presence of gravity. With his theory, different gravitational fields and different motion speeds will lead different structures and properties for the same atom or molecule. It could mean disaster for living beings dwelling on different planets or different elevations on the same planet. This could be the most fundamental flaw of Einstein's theory. Consequently, we need to find a unification of quantum theory with gravitation so that the randomness introduced by different inertial frames and different gravitational fields can be reduced to zero. Specifically, it is desirable to find out a new theory such that the sameness property for all atoms and molecules is kept in all inertial frames with or without gravity. Realizing that the discovery of intrinsic variables as the key element of learning, to reduce the aforementioned randomness, we can map Einstein's space-time metric tensor of space-time g_mu, the key concept to general relativity, to the quantum wave function propagation parameters g_mu. G_mu is the inverse of g_mu. The former is a covariant tensor and the latter is a contravariant tensor. In other words, it is proposed here that the quantum wave function propagation parameters g_mu should be the intrinsic variables we are looking for, not Einstein's metric tensor variables g_mu of spacetime. The quantum wave function is a universal constraint on the propagation of the wave function of any quantum particle in space and time. It has been discovered by physicists based on experiments and observations. The function governs the motion of all quantum particles. With the previous hypothesis, it can be proved that the sameness property for atoms and molecules is kept for all inertial frames with or without gravity. Also, it has been found by the author that the universal motion equation for a particle with a wave function psi xyzt as g_mu partial nu psi xyzt equals m square c square divided by h bar square times psi xyzt falls back to Einstein's geodesic equation in general relativity at the classical limit. That is, the new theory is compatible with general relativity at the classical limit. To be more specific, at the macroscopic scale, when each object has a finite position and velocity at any given time, each free object follows a path in spacetime which has the longest proper time s, where s is the integral of ds and ds equals the square root of minus g_mu nu dx mu dx nu. Understanding the principle of learning can help us to build next-generation intelligent systems that have the true power of the human brain, that is, the capability to figure out different solutions for different problems. It can also help us to demystify the principle behind many great scientific discoveries, and to boost our brain power for scientific discoveries when we apply the principle in a systematic way intentionally. To have equality, peace, and prosperity for human societies, we may need two more principles, namely, the principle of equality and the principle of harmony. For a society of multiple competing individuals, the principle of equality ensures that the global optimum for the entire society is also a stable equilibrium. Most importantly, the principle ensures that this global optimal equilibrium is also the best for every individual in the society at the same time. The principle of harmony offers a mechanism to reach the equilibrium. At the most fundamental levels of nature, we have those principles implemented. Specifically, relativity equals equality and quantum laws contain harmony. The former is defined by the universal motion equation g mu partial nu minus m squared times psi equals 0, and the latter by the quantum annealing equation minus h bar times the derivative of psi with respect to time equals the Hamiltonian minus the expectation of the Hamiltonian times psi. Together, they ensure the sameness property at constructing each atom and molecule in the universe regardless of time, location, the speed of motion, and the strength of gravity. Atoms and molecules are the building blocks of the universe. Without this property, the structure of an atom or molecule, say a hydrogen atom, will change from time to time and place to place, sensitive to the speed of motion and the strength of gravity. This will lead to chaos in the universe. Therefore, the two principles are indispensable for the orders and harmony of the universe.